Today's talk is about high-speed seismic acquisition using vibrators. It's the second time BP's used distance-separated simultaneous sweeping, and that was to get a really high-fold survey in the Jordan area. I just flashed my laser pointer at a screen, recognizing that the other screens behind my back and the guys in the universities listening won't be able to see what I'm doing. So I'll refrain from doing that, well, as much as I can. So the outline for this talk is pretty simple. We'll talk about the geophysical problem and its invisible reflectors. I always end up working on seismic data that no one can see anything on. We'll take a look at the survey design solution, my favorite, very long offsets, wide azimuth, parallel acquisition to produce very high fold. Talk about the operational challenges. It's always trouble getting 500 people on a crew to work together. The productivity was absolutely amazing. At the peak, it was over 50 square kilometers a day. When I started, 50 square kilometers was a big 3D survey, and in Jordan, we shot that in a day at 1,200 fold, which is impressive. The data was, well, the superlative wow isn't even good enough. It's an impressive data quality results. But let's go have a look at that. That was the agenda. Now for the hidden agenda. This was originally presented in Kuwait at a single source, single sensor workshop where they had a 250,000 unique Western GECO unique crew running out in the field, and so they wanted to have a workshop to talk about what could be done with data like that. So I started off this talk discussing seismic arrays. There's a trend in the industry now that we've moved to nodes to get rid of the array all completely and have a single sensor. And so I just want to take a kind of a look at that. We can apply spatial filtering in a variety of places in our seismic system. So because our seismic system is mostly linear, the convolution of spatial filtering is commutative. So we can apply it in the field in analog using receiver arrays or source arrays. We can apply it digitally by recording single groups as they do in Q or Unique or some of the finer sample systems, and then use digital group forming to simulate a field array. So that's the same sort of thing, except we're moving it later in the system. You can also apply just the standard stacking, either before or after migration, and that's a k=0 spatial filter. So again, it's just a convolutional spatial filter. It can also be applied in various pre-stacked sort domains. We're familiar with FK and FKK and tau P and all those other fancy velocity filters or convolutional spatial filters. Migration is my absolute favorite because it's an all-pass for all geologic dip, and it does a pretty good job of suppressing evanescent energy. So again, migration, pre-stack migration in particular, is just another spatial filter. And so the stuff at the beginning, the field arrays or DGF, I consider to be anti-alias filters to condition our data to be able to be migrated properly. Well, that's a lot of words on one slide, so let's go look at some pictures. This case history is from the Jordan area. So BP was given a concession. Let me point it out here. It's the one in red, bumping up against Iraq and Saudi Arabia. Our actual block went all the way up to Syria, and this is the first concession I'd ever worked on that had 3 international borders, which was just, a minefield, literally and figuratively. It's an area of high unexploded ordnance, and we had people crossing from Iraq in with all sorts of munitions that they'd sit on the block and take apart to be able to sell the chemicals they got out of the shells. So we had a fair amount of ordnance clearance to do before we shot the survey. But we did actually cover the whole thing with a 50 by 50 meter grid of shots, 5,000 square kilometers, which is a lot of vibration points. I'll show you how we did that. First, let's have a look at the data. I was like looking at an existing stack record. Can any of you see anything on that? Any idea where the target is? It's like where's Waldo? Yeah, it's buried in there someplace, and that was the typical data quality. What is going on here? From a stack record, it's a bit difficult to tell, other than you can say it's a no data area. And they tried drilling on that, and it had mixed success. Here's some shot records. Maybe we can see a bit more, okay? We've got ground roll and air blast and some direct arrivals, very fast on the near surface. So I'm going to clear that off, but you also see underneath some hummocky kind of aliased energy. So this part of the world has a very fast near surface, and it's karsted. So you've got dissolution of the anhydrites and some limestones in the near surface, creating fractures and faults, and in some places caverns. You could actually run the trucks across the ground and hear the echoes underneath. But no vibrators were lost in the making of this seismic survey, luckily. Those caverns and casts and faults in the near surface created a lot of backscatter. So you've got a fairly inattenuative near surface, lots of features for energy to scatter off of, and it just created a huge cone of despair in the middle of the record. When I looked at this, I knew that the fast burst breaks were going to allow me to use much further offsets. And so that's the first clue to what may be helping us to get good data in an area that had previously thwarted all attempts. So how's that done? Let's have a look at this slide. Gives the entire acquisition geometry on one page. We used 28-kilometer long receiver lines. So actually these receiver lines covered half of the block at a time. And here's a set where the vibrator is active. The maximum usable offset, I think it's a 7-kilometer circle, stretches pretty much across the whole thing. So we've got an active recording patch of 22 lines. That's a lot of lines on the ground. I think we have 12,000 channels to set this out at 50-meter spacing. And that gave enough room to actually have 3 groups of recorders active at any one time. So it was simultaneously, at any point, there were 3 recorders shaking, and in slip sweep mode, for part of that sweep, there were 6 going. So it's a 6-for-1 gain at some places. In order to make it's an exploration survey, so in order to make the production quick, we use quite wide line spacing. I think that's legitimate for a very deep target, and that's compensated in part because we have very high inline poles. Still stretched out 6 phones over the 50-meter group interval because I really like analog arrays as spatial anti-alias filters. And then the vibrators themselves, it was a single vibrator used. So the first thing, if you want extra productivity in your vibra-size surveys, break up the vibrator array. You can actually, if you have 3 or 4 in your array, put them out on individual source lines because you can make use of them, certainly in flip-flop shooting, kind of cycling through in slip sweep, or in DS cubed, or even more in ISX. So the modern simultaneous source techniques can take advantage of extra vibrators, and you get those extra vibrators by breaking up the array. So I don't have a source array, but I do have a receiver array. At least I'm partially alias protected, and that's fully compensated by this 50 by 50 meter grid. That creates really high folds. So let me cover it up with what are the salient points. 22 lines live, big line spacing, but very tight source spacing. So it's 600-meter receiver line spacing, but 50-meter source line spacing, if you were to think of it as an orthogonal survey. It's really lopsided, but there's actual benefits to that in processing, as we'll see in a moment. Some numbers, almost 5 million trace density, 1,200 fold if you like that. The bins were 25 by 25. I'll show some examples of the processing and just the final results in a moment. So I'll recover that. It was fairly high resolution for the deep targets. Because it's single line roll, fully surface consistent, fully coupled, we didn't repeat any, let me go back here. We didn't repeat any sources during the roll or any receiver positions. So it was single receiver placement, single source placement, other than the extended sources in the zipper zone. So we did repeat sources down the middle, but if the concession had been narrower, or conversely, if we had 60-kilometer long receiver lines, we wouldn't need to have repeated any stations. But the most interesting thing about that, Heisberg-Meyer calls it a hybrid survey. I call it a wide azimuth parallel survey with fully sampled source grid. You could call it megabin done with a much better source sample rate. But what it gives is a variety of 3D pre-stacked single-fold sort domains in which we can do more of that magic spatial convolutional filtering. So let me go over some of them that we can sort into with this type of acquisition. Given one receiver, and I've got it shown as a blue dot, we can collect a full source grid of 50 by 50 meter around the outside of that receiver. That constitutes, if you invoke reciprocity, a true wave field. So you can apply your favorite FK filter if you like that, tau P, FXY decon. You can sort it into two X and Y offsets and do despiking. So there's a lot of single channel and multi-channel filtering that can be done in this domain, or you could even run it into a wave field migration after preconditioning is finished with it. You can sort the data into the familiar cross-spread domain. Assume at least half the room is familiar with cross-spread filtering. And because we've got a 50-meter interval on shots, there's going to be a lot of these cross-spreads. 200 of them per linear kilometer. So it took a fair amount of time to process in the cross-spread domain. But again, you've probably from your own experiences seen the value of doing that. Then there's the common vector tile. With the high fold and relatively tight spacing, well, certainly tight spacing on the shots, we were able to get the vector tile useful in two different orientations. One of them is a CDP gather where the surface sources and receivers are in a grid. So that gives us the ability to actually do 3D processing in a CDP. Typically, you only sort CDPs by offset class. That's all you can do with an orthogonal survey because the offsets are so sparse in any one particular direction. But here, because we've got fine sampling, we can actually sort this as a true 3D grid, and it's well sampled enough to apply any of the FK filters, tau P, or the other harsh 3D velocity filters. And it's almost complete impunity from geologic smearing, because within a CDP, you don't have to worry about affecting adjacent CDPs. You can do the filtering completely in one sort domain without worrying about subsurface structure or dip, especially true after pre-stack migration. So if you use a vector, offset vector migration, and 1,200 traces into migration, 1,200 traces out of migration, you end up with a full 3D CDP sort that you can continue to do pre-stack filtering on. So most people here are familiar with using migration, pre-stack migration, near the end of the process. You finally get your data the way you like it, migrate it, stack it up, do velocity analysis, and you're finished. I like to move, especially with data like this, the pre-stack migration process to the middle or even earlier in the processing. So if I've got a 1 year long processing, I might actually run the pre-stack migration after 5 months and spend another 7 months working the output data, because I've got exactly the same fold in as out with this type of gather. And finally, there's the common vector tile. So we're familiar with common offset cubes for towed streamer. Well, with this type, we can sort each one of these offset vectors into a common offset volume that spans the entire area of the survey. So with that, it's very useful for FXY decon. So any post-stack filtering you might like to do can also be done on this domain, so despiking and FXY decon. So I'll slip back into the acquisition mode and talk a bit about a spatial anti-alias. And so the traditional method of shooting seismic in the desert with these vibrator arrays, man, they look a little fuzzy from back here, but yes, those are pictures of vibrators. Up front, there's a bulldozer and a cat push surveyor. So he'll prepare the lines through the dunes, put out a flag, the vibrators all following the lead vibrator hit the flag, vibrate on that point on the day of reporting, and a surveyor comes along at the end and picks everything up, the pin flags. So with modern equipment, you have GPS inside the vibrator. We've broken up the array so they can wander around the desert driving to pre-plot location. That freed us from preparing the trail and planting a pin flag. So now these guys just drive to the point they need to. And that means they can go around the trouble spots, go around the dunes, pick their best way up and down the wadi edges. Very, very quick. And that's one of the ways that we got the higher production as well. So I knew from work in North America, South America, that this path of least resistance method would give a lot of variability in the position of the final source points, and that would inject some random midpoint scatter in the final image. Great. I went out to scout the area and put in 2 points on the GPS and said, I'm going to drive a straight line and check the track log to see how much I have to deviate. 0. It's mostly gravel plain. So I knew right away that the vibrators would be going mostly straight until they hit a wadi, which they had to fish around. So in order to promote the idea of midpoint scatter, I came up with a slalom technique. So I'll go through midpoint scatter techniques. There's receiver and source arrays. If you have 6 or 8 geophones on the surface, you're going to get an image of those 6 or 8 geophones in the subsurface at the point of reflection. Norm Cooper promoted the alternate inline station shift. Andreas Korston, the reciprocal of that is the lateral line shift, so every second line has a shift. I actually used that on this survey. Quasi-Monte Carlos deployment, which is true random. Jerry Schuster promoted that. I like to use oblique trails and slope chaining, particularly in the foothills or anywhere where there's topography. And then variable inline station spacing. That's an odd one. That's where we're shooting survey on a lake, and so every second and third line had a different inline station spacing. So you imagine 48, 50, 53, and then back to 48. Never seen anyone else use that. It does work though. And in this case, I used a technique which I had employed in South America to go up steep cliffs. We used switchback or slalom trails. And so on this survey, I put in these wiggly lines. So there are about a wavelength of 6 sinusoids within the usable offset. The amplitude of the sinusoid was exactly 1 station interval, plus or minus 25 meters. And what that gives is a pretty good midpoint smear. I'll show you here now. So we've got all these, from the 22 lines, you get these 11 clusters of midpoints, but they're spread across the whole CDP. This is a CDP bound, by the way. And if we remember that we've got geophones on the surface, each of these points on the subsurface will be replicated again by the individual ray paths that make it to the phone. So we've got pretty good coverage over the CDP, and when that's processed, even a brute stack will apply a fairly rudimentary K=0 filter and filter off the dips and frequencies which would alias in migration. Now, this is one of my favorites. I just gaze in awe at the high fold of this thing because of the very high inline fold and 22 cross lines. We've got up over 1,200 fold at the usable design offset. And if you like to look at the offset plot, it's fairly dense. So this is going to be easy to analyze for velocity analysis. Well, assuming that you could actually make out a reflection on the processed data. So we'll move to that point in a second. Here are the vector tiles. And I'm going to spend a few minutes talking about vector tiles. They have come into vogue in the last 10 years, and they're one of the most powerful sort domains that we have available. You hardly ever get a chance to use them with orthogonal low fold surveys, but these high fold surveys, especially with the fully sampled grid, lend themselves quite well. So let me discuss them a bit. Before I move, I can say that you can see how they slightly change. These are colored spider plots. They slightly change as we move across away from one receiver line to another. So I'm going to zoom in slightly. You're going to have to squint to see what I'm going to show next. But this is one bin, which I've blown up. And each of the colored lines represents a source to receiver offset, and azimuth. And there are 1,200 of them plotted, so we can go through and, no, I'm not going to count them for you. Let me take a look at a few of the, well, next step, I'll zoom in, and in the inline direction, the distance between each of these vectors in the inline direction is 100 meters. And that arises because we have a source spacing of 50 meters in the inline, receiver spacing of 50 meters, and so for any adjacent offset, you have to move the source away from the receiver, which accumulates to 100 meters. In the crossline direction, it's a lot worse because our line spacing is 600 meters. We move to the next line, which means we have to move down to the next shot to get it, and we have a 1,200 meter offset interval. So that's a bit coarse to use for any kind of filtering. Almost everything is going to alias at that 1,200 meters, although it's quite stable at 100 meters, and that's a great offset increment to use for dipping noise attenuation. To try and alleviate some of that alias criteria, there's a concept called folding, and that's invoking reciprocity and saying if I have an offset azimuth in this direction, I can artificially place it up in the other direction. So let me draw 3 of those and move them up. Everyone catch that? I'll do it again. There are 3 vectors here, and I'm going to pick them up and move them up top. The advantage of moving them in this case, in this type of geometry, is that they happen to fit in between 2 other lines in that quadrant. So I can take this quadrant, move it to the top right, the bottom right quadrant, move it to the top left, which I'll do here in a second. And by doing that, I can interleave, just because of the way the vector tiles fit, this group in here, and actually create a half-sided, or 0 to 180 degree azimuth, but more finely sampled vector tile data set, which is more conducive to putting into either FK filtering or tau P, high-res tau P. So let me show that again. Here's the various vectors from these 2 bottom quadrants moved up to the top right. And what I'm going to claim next is that this acquisition geometry provides yet another benefit. And probably everyone's heard of the Anstey stack array. It works well in 2D if your shot group interval equals your receiver group interval. And a lot of people have proposed methods of applying Anstey stack array in 3D, but it's just prohibitively expensive to lay out aerial receiver arrays and source and receiver grids. So my claim, my brash claim for this afternoon, is that this type of parallel geometry allows some of the Anstey stack array benefit within these yellow quadrants. And so let's have a closer look. So I'm going to zoom in on this area. This is a ball plot, I think, in Mesa, and these are 100-meter intervals. And I like the ball plot because I'm using it as a proxy for if I had a shot here, a vibrator on the surface, and we got it emitted ground roll, then these could be a proxy for the expanding wavefront. So bear that in mind. You can see in the inline direction that the wavefront's almost perpendicular, and because I've got even number of shots of receivers, I'm actually going to get a pretty good Anstey stack array just on those 2 inner lines, because it looks like a semi-broadside 2D. So there I'm propagating my ground roll. It's impinging at a slight oblique angle on the receiver line. So I'll zoom in, and it does pass the receiver line at a slight angle. And the way I look at the sampling criteria for that, there's a foreshortening of the receiver interval and shot interval in the direction of the propagating wave. But the nice thing is, because I've alias protected that with an analog receiver array, it foreshortens at the same rate. So in fact, this slight angle works if the whole waveform is collected along the receiver line. If you stack up just those inside lines, the Anstey stack array holds, and the ground roll is gone on the stack. You cannot detect it. You have about 40 dB noise attenuation. What about the further outside lines? Well, for the near ones, the same technique applies, and you get a foreshortening, it's a much more stringent foreshortening. And so for one section of this line, you do get a fairly good Anstey stack array. For the direct cross lines, they are broadside to the receiver array, and the interval between lines on the surface is 600 meters. And so there's, in the CDP domain, it's 1,200 meters. So it's just very, very leaky. So what's happening at, say, this 45-degree angle, 50-degree angle? We get segments of good Anstey stack array attenuation with gaps. So imagine you took a 2D line, perfect stack array, and just took gaps of it out, let a little bit of leakage. It's still a reasonably good attenuator, but you get edge effects. And so what we found is that just stacking it up, because of the dominance of inline to crossline, our patch tends to be that way anyways, that we don't have to worry too much about residual ground roll leaking through the stack. This is, when I say stack, I mean pre-stack, migrate it, and stack afterwards. Yeah, I can see some disbelief on the faces. Wait till you see the final images. Sorry, I don't want to steal my own thunder. So, parallel versus orthogonal. I know Alberta mostly uses orthogonal acquisition, and that's because you have line clearance. What can you do? You can't have a 20 meter by 20 meter grid of shots or receivers that you run into a real line clearance problem. So orthogonal, I picked a fairly tight one, 200 meters by 200 meters, which is actually used quite a bit in the Middle East as well, with a tight station spacing, 25 by 25. Well, the vector tile map of that is fairly high fold at whatever offset range I chose here. You can see lots of these vector tiles, but it gives you a 400 meter interval in offset in any direction. And that's because you have a 200 meter line spacing in both directions. And that's a bit tough to use for filtering. You could really only filter 15 hertz and below without aliasing. Anything above that is going to alias. So you can't really apply FK filtering. What about folding? Hey, maybe that'll get one dimension down to 200. And so I took a look at the vector tile map and tried folding these three vectors across. And sadly, because I chose a bin very near the center, that vector exactly mapped on top of existing azimuth offsets. So for orthogonal, especially even line spacing, symmetric sampling, the vector tile folding doesn't work as well. You tend to replicate existing offsets. So you may be able, if you're partway between the lines, to get some offset between them, but it's not as clean a sort. You can't really make the assumption that you have half the interval in one direction. So switch from parallel to, or from orthogonal to parallel if you can, and I'll throw that challenge out to the room and come back in 5 years and see how you've done. Again, just to replicate in the parallel, we really are going to moving the offset vectors to new locations. So simultaneous sources, and I'm going to jump into that and explain how DS cube works a little bit. My colleague Dave Howe invented independent simultaneous sweeping, which is just randomly letting the vibrators go, allowing all of the interference into the record and dealing with it in processing to attenuate the interfering sources. Craig Beasley, about 20 years ago, suggested using shots on either end of a marine cable, and you get interference, and then using the conflicting dip and heavy dip filtering to attenuate some of it. My extension to this was to take the vibrator array, which might be within 15 meters of each other, and separate them to a long distance, in this case, 12 kilometers. So now these are independent vibrators, and if I sweep them, I'm going to start emitting the ground roll and the reflection energy. And at the point where the ground roll and the subsurface crosses, then I'm hoping, if I've set my distance wide enough, that interfering energy will be below my zone of interest. So in this case, we did it with using 3 vibrators on Jordan, with a very small amount of overlap at the zone of interest. Notice this is all very clean data. There's no interfering vibrators here. So most of the time, over most of the traces, there's no interference seen at all, and only in the small overlap zone at the base of the records do you have anything. This produces really, this is actually from Oman, so this produces very clean data over our zone of interest. And we can actually take these records and this is two records, although they're both combined. One record will have the XY coordinates of the shot here, and then you get exactly the same record, but in the headers you have the XY of the shot at this position. So these two records are the same data. They go into processing. You don't even have to tell the processors that it was shot simultaneously. They just bring it in, apply an offset mute. They never know about the interference because it's unimportant. So here's the data from Jordan shot with the S-cubed. Here's the three vibrators. And can you make anything out on that? I'm going to stare at the laptop screen and there's hardly anything. Yeah, this is a really bad data quality area. I'm going to have to draw things out on the PowerPoint for you to sort of be able to see where that's the ground roll cone. I think the first breaks come through about there. This is just horrible data. So long offsets and high fold to the rescue. Here's how the data was shot. It was actually shot 24 hours. So Oman was the first country where we used 24-hour recording, and Saudi had been doing it for years. And then Jordan, we went with 24-hour recording because we had ordnance clearance on the lines to make sure that it was okay. So what's going to happen here is these three vibrators are linked together in the doghouse. They're 12 kilometers apart, so I can vibrate each of them simultaneously, and they start moving. As soon as they've finished enough of their slip sweep, the next vibrator down the line starts moving, or starts sweeping and then moving after it finishes. And when the last one's finished, the first one starts again. So in this case, I've got like continuous energy going in the ground, plus the slip sweep aspect of it, plus it's happening at two other locations. So it's between 6 to 1 and 10 to 1 times more quickly. In the animation, what I didn't show is that we had an extension to the Sercel 464 controllers for Jordan, and so we were able to dynamically fleet. So on the second pass of this animation, you can see some of these vibrators don't have to pick up their same mate. If this guy gets delayed for some reason or a detour, then it can pair with any vibrator that's available with pad down that is 12 kilometers away. So that helped increase efficiency quite a bit. So if a vibrator went down, broken, it didn't stop production. The other vibrators in the pair just started picking up new vibrators to fleet in. We used slip sweep, and it was aggressive slip sweep. In other words, we started the sweep all the way through the listen time. So essentially, there was no gap in quiet listening. It was continuous overlap. And then once it went through the cycle of 6 vibrators, it was up to the next one. So again, I say it was shot with a zipper. So that means we shot one side of the survey starting at the north, proceeding south. These are the receivers cutting halfway, and these are the shots. And then we shot the second half by moving the receiver cables around to the bottom and up the other side. Productivity after the learning curve was pretty good. Can I read any of this? 18,350 was the peak sustained production. And we had, I think, a peak day of over 20,000. I can't find it. There it is, somewhere in there. And that number is like 22,000. 22,000 records in a day. It's a lot of tape. I'm tempted to ask the question, how many people designed or worked with a 3D survey that has 22,000 shots in it? They're pretty rare. We shot that in a day. Right, this is one where other crews were phoning their friends on this crew asking if what was happening was actually true. Are you guys really getting that much? So this helped spark the rivalry in the Middle East. Who's got more records than anyone else per day? Fortunately, there were no prizes given out, and I get to show the graph. So to illustrate how fast this actually goes, I've come up with a mythical horse race. They're not horses, I'm going to use vibrators. In this case, I've got a conventional vibrator, independent simultaneous sweeping on the inner outer tube, and then a couple of distance separated simultaneous sweeping. So again, this is Jordan, Oman, these ones are Libya and Algeria, and this is Algeria. So pay attention. Remember, this is just a demonstration, not a competition. Please, no wagering on the outcome. And so they're off. And straight out of the box is the Jordan vibrator. First around the bend is Jordan, followed quickly by Oman, and Jordan finishes the race first. So just as an illustration, DS cubed is that much faster. Had we shot conventional, by the time the DS cube vibrators were finished, we would have only gotten less than a quarter of the survey. Very impressive. ISS, these were both run daylight only. So if you turn on 24-hour recordings, the ISS and DS cubed are neck and neck. Let's go to the final results. I know that the horse race is a little bit exciting, but we have to look at boring data here for a second. And the reason it's boring is because if you were the interpreter, you'd be scratching your head. Yeah, I can see these are 2D lines, and I think I've got an old 3D here. That 3D was shot with just short offsets, 0 to 3 kilometers. So essentially all of the data was collected in that no data cone of despair in the ground roll. So there's nothing they could do with 60-fold data. They couldn't stack it up. They couldn't really process it. The 2Ds had giant receiver arrays on them, which did help attenuate some of the inline backscatter and ground roll. And plus, I think this 2D line had further offsets than the 3D. So that's the brute stack, our fast-track brute stack in the new 3D. There's just no comparison. You can actually interpret that. So let's have another look. The new brute stack, so that's the old 2D, old 3D, had longer records. So for the first time, we're seeing the true basement structure. So that's an advantage. If you like color scales, which don't show as much dipping noise, but show more speckle from the aliasing, here's the old 2D seismic, the old 3D seismic, and the new 3D final processing. Targets in here. Compare it to the old stuff, uninterpretable. How many people here want 1200 fold data? Yeah, I know, I'm not going back. So there's the records that we acquired in Jordan. There's the first breaks, and you don't see very much underneath it. How much processing do you think we did to get AVO attributes out of this, and what would they look like? Well, long offsets 1200 fold to the rescue. Using the AI-GI technique from BP, just using well log information, we found that there's a very good, if we project on this line, that there's a very good separation between sands and shales. Here's the P wave, and as we move across, we go from shale to a sand regime, which is the reservoir, but it's a bit invisible on the AV or on the P wave. So let's make sure I get this right. No, sorry. This is the impedance volume, and this is the P wave. So where it's highlighted in yellow, we lose reflectivity, but on the AVO, we gain that reflectivity. I think it's more impressive in map view. So this is attribute extraction from the fast track, reflectivity from the pre-stack time migrated volume. So these again are amplitudes extracted. And you can see a line through here, but when you run the AVO and color it up, this colors up as sand and this is shale. Extremely clear demarcation of the lithological boundary and amplitudes to give us an idea of thickness within it. So, in summary, I didn't use up all of my 60% technical time. But you'll have lots of chance for questions, and we can go back through the slides and look at them in detail should you not wish to go back to work on a Friday afternoon. But I'll just sum up the blatantly obvious, the nose on my face. So the DS cubed and ISS approaches allow us to start shooting densities of data that were just unimaginable before. The small amount of interference is immaterial. Now, high-fold land seismic is worth its weight in gold. This is only $6,000 a square kilometer. Yeah, sorry I said that. It ruined your afternoon. And those fully sampled source wave fields, I can't promote them enough. They really helped us both in the Oman, Libya, and the Jordan surveys. So with that, I should acknowledge all the people that helped. You'll see there was a co-author on this, Jonathan Stone, fantastic project manager who spearheaded some of the early work on the acquisition design, and all these other people helped as well. Chris Pearson, Martin were the interpreters who produced those images at the end. And with that, the last group to thank is you. Thank you very much for your attention.